Hey everybody, welcome to today's video about cations and anions. Let's start by talking about cations, which are positively charged ions. And I'd like to start with an example of sodium. Sodium metal atoms have 11 protons and 11 electrons. Those 11 electrons are found in 3 different energy levels. So this part is, of course, the electron configuration for the sodium metal atoms. But let's suppose that some energy is used to overcome the Coulombic attraction between these protons and this outermost electron. And as that energy is applied, the electron can be physically removed from the atom. If that happens, then we no longer have a neutral particle because while we still have 11 positive protons, we now have only 10 electrons. So that is now a sodium 1 plus cation. And this is the electron configuration for the ion. Okay, now let's talk about size. You can see from the electron configuration of the ion that it's shorter than that of the atom. And if we look back up here at our picture, when we considered the neutral atom, there were 3 occupied energy levels, but the ion had only 2 occupied energy levels. So we find that that's true for all cations. Cations are always smaller than their atoms. And this is how I'd like you to think of that. In the neutral atom, the proton to electron ratio is 1:1. Same number of protons and electrons. But in forming the cation, the protons stayed the same, but we reduced the number of electrons. So this ratio is now greater than 1. And Coulomb's law would tell us that if the charge ratio is larger, the force of attraction is stronger. That means that the electrons are going to be held more tightly to the positive protons, and they will all be closer to the nucleus. Remember when we talked about trends in metal atom sizes, we said that as you go down a group, you're adding additional energy levels and the atoms get bigger. The same is true for the cations going down a group. And notice in each case, the cation is always smaller than its atom. Okay, one more thing I'd like to talk about. I'd like you to be able to write an equation for ionization energy. So again, if we're considering our sodium atom, when ionization energy was applied, the atom turned into a cation by losing 1 electron. Notice we only lose 1 electron, and now the ion is 1 plus. The ionization energy that's needed to do that is 496 kilojoules, and it is a positive quantity because remember, energy must go in if you're going to overcome forces of attraction. Okay, this electron was coulombically attracted to the protons in the nucleus, and we had to put energy in to overcome that coulombic attraction. Now, that's called first ionization energy because it's the energy needed to remove the first electron, this one right here. But once that electron is gone, is it possible to remove any of the others? And the answer is, yeah, it is possible. So if we're going to start with our sodium cation, we could put some more energy in and create a 2 plus cation. And here is the second electron that has been removed. Now notice that the second ionization energy, the energy needed to remove a second subsequent electron, is much, much larger than the first. And that's always going to be true simply because the Coulombic attraction gets stronger and stronger as you remove electrons. That proton to electron ratio, that charge ratio, keeps getting bigger, so the force of attraction gets stronger. Okay, now let's turn our focus to anions. And let's consider the fluorine atom with 9 protons and 9 electrons. Okay, this is the this is the electron configuration for our fluorine atom. We see that the electrons are occupying 2 energy levels. Now, let's suppose that an electron was added to this atom. So here comes an electron from somewhere else, and it's going to be added to this atom. In that case, we'll still have 9 protons, but then instead of 9 electrons, we're going to have 10 electrons. And that gives us an electron configuration like this. And this is no longer a neutral fluorine atom, but because it has 1 extra electron, now 10, but still the 9 protons, this is an ion with a negative charge. Anions are negatively charged ions. So again, electron configuration of the neutral atom, which you can determine easily from a periodic table. And then I also want you to be able to write an electron configuration if an ion is formed. In the case of forming an anion, you're adding additional electrons. Let's talk about the size. Now, this one may not be quite as intuitively obvious, but anions are always larger than their atoms. Again, in the neutral atom, the proton to electron ratio is 1. But in forming an anion, the proton number stays the same, but we're adding electrons. That causes a proton to electron ratio to be smaller than 1. And if the charge ratio gets smaller, the force of attraction gets weaker. There's one more thing at play here. When you add extra electrons to that same energy level, there's extra crowding, and they're going to repel each other. So back up here, we had 7 electrons in this second energy level. And if we increase that from 7 to 8, the addition of another electron to that same occupied energy level gives some extra repulsion, and things just kind of swell out farther from the nucleus. Okay, so looking at trends, we said that non-metal atoms get larger as you go down a group, and the same thing is true for the anions. They get larger as you go down the group. Again, though, each anion is larger than its atom. All right, and then lastly, let's talk about equations for this process. This is going to be called equations for electron affinity. So the one I described to you showed a fluorine atom gaining an electron. Notice electron is on the reactant side this time. And when a neutral fluorine atom gains an electron, it becomes a negative anion. And that process has an enthalpy change that corresponds to it, known as electron affinity. Would you take a minute to read and write down that definition? Electron affinity is the energy change, this change in enthalpy, that's associated with gaining an electron. And sometimes it's exothermic and sometimes it's endothermic. So you remember we learned that when particles attract to each other, energy is released. Well, that's what's going on in this process. This negative electron is very attracted to the protons in the fluorine atom. Fluorine is tiny. It's got its 9 protons. This electron is attracted, and so energy is released. And that process, that electron affinity, is an energy change that's exothermic. But adding electrons is not always cause for attraction. There are some instances where a neutral atom doesn't really want, I'm using that in air quotes because of course atoms don't have feelings or desires, but metal atoms are not likely to gain electrons and become anions. It can happen, but it's a force fit, in which case the energy change involved would be endothermic. Energy has to go in. What I want you to understand is that equations for electron affinity are sometimes exothermic and sometimes endothermic. All right, so to sum up, you should be able to write equations for electron affinities and also for ionization energies. Remember that the ionization energy process, sorry, I'm losing all my pieces. Ionization energy is always an endothermic process, but electron affinity is sometimes exo, sometimes endo. I also want you to be able to write electron configurations for either metal atoms or their cations, non-metal atoms or their anions. And of course, recognize how the size of an ion differs from the size of its atom. Okay, guys, hope that was helpful.